I hope right now you can concentrate on this workshop, which sounds very promising, very topical indeed. So I pass over. Thank you.
Thank you very much. I think we also want to start like thanking the Newton Institute for hosting computability, complexity, and randomness for the second time. And this second time has taken maybe a bit more of work because it's been 2 years since we were going to organize a CCR here, but luckily they haven't given up on us and they kept helping us all the way up to here. So I'm really happy that there are more people in person here than I even thought. Thank you very much to all of those that could come and to all of you that are online listening to us. And let's just start with the first talk. We'll keep talking. Thank you very much, Ulrich. So we're starting with Selwyn Ng with the algorithm strength of planar graph coloring theorems. Thank you.
Thank you, Elvira. Yeah, so first I'd like to thank very much to the organizers for inviting me, and I'm very sorry that I'm not able to make it in person due to certain circumstances, but I hope eventually, I can get to travel to conferences and then see everybody. Right, so what I'm going to be talking about today is graph coloring theorems. And this is going to be quite similar to a talk that I've given in Lumini. So I'm very sorry if you were there. But I will try and maybe focus a little bit on the details that I didn't get to the last time, so that in case you've seen the talk before, you have something new to take away today. So yeah, so we're going to be talking about the coloring of graphs. And of course, I should point out that computable graphs have been studied for a very, very long time, and even as early as the 70s, due to the work of Bean and Schmerl. And of course, it also appeared quite a bit on in Jeff Hurst's thesis, and also there's been quite a bit of subsequent work. So all work is joined with Ko, who is a student of mine. So the theorem that that leads to this investigation is due to this surely very famous theorem of Appel and Haken, that the 4-color theorem. Every simple planar graph can be colored with 4 colors. And we're going to be asking ourselves what the algorithmic strength of the 4-color theorem is. So well, this whole thing started, of course, with the question about coloring of maps. So if you have a map, of course, you can associate that with a planar graph, and the coloring of the map, of course, is the same as the coloring of the associated graph. So here is a map of Europe. Well, I've kind of resized it so that it fits on the screen. So I hope that nobody is offended if I've kind of cropped off the region that you're from. But here in this particular instance, we have Austria and the Czech Republic, Slovakia, Romania, and Ukraine, which are all neighbors of. Oh, I'm sorry, I messed that up. Sorry, no. What I meant to say was, we want to look at Slovakia, which is bordered by 5 neighbors around it, and Slovakia is kind of in the middle. And so in this particular coloring, we see that the neighbors are arranged so that each of the neighbor is kind of adjacent to the to a neighboring one if you arrange them in a circle. So that means that if you're coloring, for example, Hungary with red, Ukraine with blue, and Poland with red, and the Czech Republic with blue, and that means that when you're trying to color Austria, you have 3 colors to avoid, and that means that you have to necessarily use 4 colors in this particular map. But however, so that means that this map cannot be colored using only 3 colors. However, you can do it with 4 colors, as is shown here. So Francis Guthrie proposed this as far as is known, this conjecture was originally traced back to him while he was trying to color the map of England. And the story goes that he asked his brother this problem, who was at that time a student of De Morgan. And of course, De Morgan being the famous guy at that time, he kind of brought this problem and popularized it. So eventually it became quite popular, and of course, as with popular problems, there have been like several incorrect proofs. So Kempe and Tate gave incorrect proofs at the time. Why they were notable was because these were of course famous people with incorrect proofs, and they were subsequently proved that their versions of the proof would subsequently turn out to be incorrect. And he would actually gave a counterexample that Kempe's proof could not be possible. And then he developed the counterexample. Using the counterexample, he developed a proof of the 5-color theorem, which is the same as the 4-color theorem, except that you were allowed 5 colors. And as of course the rest is history, as we all know, eventually this was finally proved using computer-assisted methods, and there were a lot of subsequent work on that. But the modern version was given by Robertson, Sanders, Seymour, and Thomas in 1996, using a much simplified method that is much more accessible to the general audience. Okay. Yeah. So let's start out with just the 5-color theorem. So the 5-color theorem, it can actually be proved much more easily than the 4-color theorem. So I just want to quickly talk about this thing. So if we had a planar graph, so as with most proof, this is done by induction, and by the Euler, this characterization of these faces and edges for planar graphs, we can deduce that there is a vertex where the degree is at most 5. So here is such a vertex, and if you remove this vertex, we assume that we can color the rest with 5 colors. So I've labeled the vertices with the 5 colors 1, 2, 3, 4, 5, and our task is of course to fill in to decide some suitable color for the vertex in the middle. Now, we look at what is called a Kempe chain, which is a path originating with this vertex that has been colored 1. But in the chain, you have an alternating sequence of nodes that are colored 1, 3, 1, 3, 1, 3. And of course, if there is no chain that starts with 1 and connects to 3 here, then of course we can just very simply, by reversing the colors on every chain originating with 1, we can switch this color from 1 to 3, and that frees up color 1 we can use for the center vertex. So the difficult case is obviously when you do have such a chain of alternating 1 and 3 colors, starting with 1 and connects to 3. But that of course means that if you now look at the 2-4 chain, there cannot be a connection from 2 to 4 because of the planarity of the graph. And that means that you can now reverse the colors 2 and 4 for this guy. So yeah, so if you had 5 colors, this was going to be much simpler than the 4-color theorem. Right. So in the subsequent discussion, I'm going to consider only simple graphs, so no loops and no multi-edges. But a graph in general in our discussion may or may not be connected, so you could have different components. K-coloring is going to be one which colors vertices. Now there's some related work on the coloring of edges, which I'll just talk about briefly, but we will just look at coloring of vertices. And of course, we consider infinite graphs, and of course, we just by the usual compactness, argument and so on. You can show that an infinite graph is K-colorable if and only if every finite subgraph is K-colorable, and this version we call locally K-colorable. Okay, so I'm just going to quickly just mention some related work in the literature. In Hurst, I believe in his thesis, he showed that the theorem over here was actually equivalent to WKL, and this was improved subsequently with work with Gersach and later by Schmerl to relax the parameter here. So originally we have k and k here, then you can actually have k and 2k minus 1, and then k and then any subsequent larger m. So of course, it's much harder to reverse if k and m here are far apart. Bean, of course, at that time did a lot of work on computable graphs and coloring in particular. So he showed, for example, as a sample of the stuff that he had considered that every k colorable computable graph has a low k coloring. Of course, the word low here suggests the use of the low basis theorem, and indeed that's true. You just have to figure out a way to represent vertices on the nodes of a tree, and then the edges of the tree will encode the possible color. Now, since we're only considering k colors, that means that the tree will be finally branching, and you can take an infinite path, infinite low path. And obviously, any computable two colorable graph has a computable coloring, because you can just start with a node and then you color all of its neighbors a different color, and then all of the neighbors are like the first color, and so on. And you should not run into trouble as you color the rest of the graph. However, Bean then showed that there is a computable three colorable planar graph. This is important, such that the graph has no computable k coloring for any k. So immediately from this, we know that the four color theorem is not computably true. In fact, the k color theorem is not computably true for any k. So this kind of sparks off the interest that we had and motivated the subsequent work. Okay. So there is a related a notion that have been considered during that time, which is that of highly recursive. So a locally finite graph. Locally finite means that every vertex has got finite degree. Is highly recursive if, first of all, it's computable graph, and secondly, the degree of each vertex itself is also computable. So highly recursive graphs give a lot of information, because you could require for all the neighbors of a node or of a vertex to be computed at any time. So Bean then proved some certain theorems about separating pi01 classes and encoding them into highly recursive graphs. So I don't really want to discuss too much this, but anyway, there were some relationships already being established between Weihrauch's lemma and graph coloring principles, even as early as Bean's work. Bean then showed that if you look at highly recursive planar graphs, however, so in contrast with his previous theorem about having a computable planar graph with no computable k coloring, he actually showed that if the planar graph is highly recursive, then there would actually be a 6 coloring of every highly recursive planar graph. And then he asked this question, which, as far as I know, it's still open, whether every highly recursive planar graph has a computable 4 or 5 coloring. This, I believe, is not known. So yeah, so I'm going to just leave it out there. Yeah, so in some related work, Schmoll shows that every highly recursive k colorable, so if you drop planar, but just look at k colorable graph, highly recursive, then there is an upper bound. There is always a computable 2k minus 1 coloring, and the result is sharp. And Kersted shows that every highly recursive k colorable, if you add in the assumption of perfect, a graph is perfect if every finite set graph can be colored in the smallest number of color that's possible, has a computable k plus 1. So you can go from k to k plus 1 if you assume that your graph is perfect. Okay, so I'll just quickly mention some work and some questions on edge coloring, even though it's not really the main focus of our work. So Kersted shows that every highly recursive k edge colorable. So basically, his previous theorem holds for edge colorable or edge coloring of graphs. So k edge colorable perfect graph always has a computable k plus 1 edge coloring. And I also want to mention this well-known theorem of Weihrauch's, that every k regular. So actually, his theorem is a little bit stronger. Is every less than or equal to k regular graph, has a k+1 edge coloring. Now, combined with Kersted's results, that means that every k regular graph has a computable k+2 edge coloring. So this we know, every computable k regular graph has a computable k+2 edge coloring. And Schmerl shows that you cannot replace k+2 with k, namely, in fact, that there is a 3 regular graph with no computable 3 edge coloring. However, he then asked the question whether Weihrauch's theorem is computably true. So namely, is it the case that every computable k regular graph has a computable k+1 edge coloring? And again, this, as far as I think, this question is also not known. So here's I'll just put the second question out there. And finally, I just want to quickly mention Carl's work, which is unpublished, that if you look at Koenig's, what's called Koenig's line coloring theorem, which is basically the same as edge coloring, but with the graph being bipartite, then if the graph is bipartite and k regular, then there's always a k edge coloring. And this statement is equivalent to Koenig's lemma. Okay, yeah, so I'm just gonna now move on to planar graphs. So all graphs considered again are simple and they don't have to be locally finite or connected unless I say so. And again, all results and definitions are over the usual base theory. Now, I'm going to just take this as the definition of a planar graph if neither k33 nor k5 appears as a minor of G. Now, of course, it is well known due to theorems of Wagner for minor and Kuratowski for subdivisions that for finite graphs is actually equivalent to having a plane embedding of the graph. Now, you can just very easily check that this can be proven. You can do this in RCA because there is minimal induction that's needed. However, the question of infinite graphs then becomes quite interesting. So for infinite graphs, we are going to represent the plane diagram or the plane embedding of a planar graph as a countable set of rational coordinates on the plane. So we're going to do all of embedding on a plane with rational coordinates. And the edges, I'm going to allow edges to curve around obstacles if needed. So each edge will be made up of finitely many line segments just to allow them to avoid obstacles. Now, of course, there is a theorem that says that every such plane diagram or every such plane embedding can be converted to one with straight lines as the edges. So there's some work done for finite graphs and then Formalising for infinite graphs. So they show that this is true for infinite graphs. However, I will not require the plane diagrams to have straight lines because that's a lot harder to do. I will discuss this a little bit later in I think on my last slide. Okay, so so here comes the statement. So it is known, of course, that again, due to the usual compactness argument, WKL from WKL it follows that every planar graph has a plane embedding or a plane diagram. The question is this computably true? And I'm just going to quickly just to illustrate what's the kind of things that we do here. It's quite easy to show that this is not computably true. There is a computable planar graph with no computable diagram. And so what we do is we set up these gadgets initially with 6 vertices, V0, V1, V2, V3, V4, and V5 over here. Now remember what we are supposed to do. All we need to do is to make our graph computable, and we have to defeat computable diagrams. Of course, our diagram doesn't have to be computable. We just need the graph to be computable. And what we do is we set up the graph with gadgets in this way, and then we watch what the computable plane diagram does, or what the computable plane diagram, how it represents our 6 vertices here. And of course, there are there's 4 possibilities for this particular gadget, whether V5 and V4 are both on the same side or on different sides of the face represented by the square. So here V4 and V5 are both outside. Here they're both inside, and here we have these two other possibilities. So depending on what the plane diagram does, we can kind of do the opposite. So for instance, if V4 and V5 appears in this way in the computable diagram, what we can do is we can put V6, we add one more vertex in the center here and connect it to V0, V1, V2, and V3, and also to V5. Now, of course, our diagram doesn't have to be computable. This gadget can be made planar just by moving V5 inside here. But of course, in the computable diagram, this cannot be moved. And then you can see that there is no way for the computable diagram to be extended to a representation of V6 because you cannot put it inside because then there's no connection to V5. You cannot put it in this face because there will be no connection to V3, and you cannot put it on the outside because then there will be no connection to V1. So in fact, one can generalize this little trick to show that WKL is equivalent to the statement that every planar graph has a plane diagram. So that means that if we are working over Wittgenstein's lemma, we will just interchangeably move between the different definitions of a planar graph. Right, so here are the principles that we consider. COL is the K-color theorem, which is the principle that every planar graph is K-colorable. So here there are no restrictions on the graph except for planarity. So the graph could be connected or not, or it could be locally finite or not, or it could have a computable diagram or not. And COL star is the version with where the graph also has to be given a computable diagram, and connected K-coloring theorem is just the one where we require the graph additionally to be connected. So for most of the rest of the talk, I will just actually be referring to the K-color theorem, but the other two principles have also been studied. Okay, so recall this result by Bean. There is a computable planar graph that has no computable K-color, so that means that the COLK is not computably true, but it actually does still follow from WKL. And as a first exercise, let's just discuss this theorem quickly. It's not that difficult to show that the 4-color theorem, in fact, the other two variants as well, actually can be reversed to WKL. So how do we do this? What we have to do is that given a tree, we want to kind of encode the tree as a graph. So what we do is we basically we repeat this particular gadget with N0, this N, the empty string, N1, and this F, and this V and W here, these six nodes here, and we kind of repeat them by connecting them to this vertex N0. We repeat up here, and with N1 we repeat another gadget, and obviously, as you might imagine, N empty string stands for an encoding of the empty string, N0 stands for the 0 extension, N1 stands for the 1,1 extension, and so on. And here, of course, we have an infinite connected graph, planar. And the encoding proceeds in the following way. So we watch, for example, some node sigma where the 0 extension dies. If the 0 extension dies from our tree, what we do is we simply add 3 nodes, 2 on the side that connects to the 0 extension node, and only 1 for the side with the 1 extension node. And note that we actually connect them to form a new K4 in each phase. And here we have 2 K4s, of course, in this phase. And now it's easy to see that if you have any 4 color of the entire graph, then because we actually have a K4 here, 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 and here, so we have to fill in with the 4 colors, 0, 1, 2, and 3. And then now for this white node over here that connects to 2, again, because of similar reasons, it actually has to be colored with the remaining color 1. And by a similar argument, the two white nodes connected to 1 also can be seen that to have the remaining colors filled in this way. So actually, it's not that difficult to see that in this gadget, any 4 color of the graph has to have the property that the 2 black nodes in the middle here has to be colored the same as the 1 extension node up here. Conversely, if we had done it the other way around, if we had added the 2 new white nodes here and the single white node over on the left, then the 2 colors here would be the same as the color of the 0 extension node. So simply by looking at the 4 color on the original set of nodes, which are the black nodes here, one can deduce at an extension which will never be removed from the tree. So that's an easy encoding of the tree into the graph. Okay, so from this we can deduce that the 4-color theorem and its variants are equivalent to Weihrauch's lemma. The interesting question comes when we consider k equals 5. In this reversal above, we used very essentially the complete K4 graph to force the color of the constructed graph to have basically to have no option. Now, of course, if your graph has got 5 colors now, obviously we cannot use K5 because the graph has to be planar. So we cannot use the same trick to reverse. So something else has to be done. And in fact, the K color theorem can be reversed, except that we have to do it not uniformly. And for K at least 7, this is provably necessary. So there is no uniform reduction for K greater or equal to 7. So instead of reversing to WKL, we will consider the DNRK principle. Recall that the DNRK principle is simply the one that says that there is a function with range amongst 0 to k minus 1 that avoids the universal partial computable function. Okay, so let's discuss how to reverse the 5-color theorem to DNR3. So again, what do we have to do? We have to produce a computable graph such that every 5 color of the produced graph will decide a DNR3 function. Again, we have these gadgets, except that we have to do things a little bit differently now. We start with these 18 nodes. We start with 6 sets of triangles, and we group them into the three triangles on the left and the 3 triangles on the right. So this is our starting gadget for encoding phi EE. And then we wait for phi EE to converge. If it doesn't converge, then of course we don't add any more nodes. But if it converges, then it can be one of 3 values, 0, 1, or 2. And in each case, we add new vertices in a different way. So first of all, if it converges to 0, we add 6 new vertices represented by the white vertices here, and each vertex will connect. Each of the new white vertex will connect to one of the triangles from the original set here, here, and here. And then we again group up the 6 new vertices into 3 triangles amongst themselves. So this is what we do if phi EE gives us 0. If phi EE gives us 1, we just introduce 2 new vertices, and one of them just connects to all the original nodes in the first set of triangles, and the second one to the second set of triangles. And if phi EE is 2, we just simply add 1 new vertex and connect to everything in the old set of nodes. So that is our graph, and it is easy to see that given any 5 coloring of the graph, we can kind of decide a suitable value that phi EE cannot take. So first of all, if the left set here these 9 vertices here are colored with only 3 colors, then it's easy to see that the first situation cannot be true, because if this set of 9 nodes are colored with only 3 colors, then these 3 white nodes will have to avoid, like this one has to avoid the 3, this one has to avoid the same 3, and this has to avoid the same 3, but then these 3 white nodes have to avoid each other, and this cannot be done with only 5 colors. So if that's the case, then we know that phi EE cannot be 0. Similarly, if the left and right together are colored with 4 colors, then we know that the second configuration is not possible, because this white node will have to avoid 4 colors, and this will have to avoid 4 colors, and then they have to avoid each other. But again, it's going to be done with 5 colors only. And finally, if all the black vertices are colored with all 5 colors, then of course the third configuration is not possible. So what this says is that if I have any 5 colors of the original set of black nodes, then we can decide a suitable value that phi EE does not take. So this allows us to avoid phi EE. Okay, so that basically says that 4 and 5 color are reversible. Now, what about 6 colors and so on? So already here there is an interesting situation, because for the 4 color theorem, we kind of reversed it uniformly, and for 5 we kind of reversed it to DNR3, which as we know is not uniformly reducible, equivalent to WKL. So here already we have some kind of a hint of non-uniformity. So this then generated some questions, and as usual, if we want to calibrate the complexity of statements, which might be equivalent in the reverse math sense, what we normally do is we would use the tools from computable analysis. So I think this definition is probably pretty well known, but this was first suggested. But really the notations came from computable analysis. So to respect the original literature, I will call this a Weihrauch reducibility, and SW to be the strong Weihrauch reducibility. So if you have pi12 statements of second order arithmetic, we can kind of think of it as the universal quantifier to be the input or an instance of a problem, and then the existential as an instance of the solution. So if we think of it this way, then the function or the partial multifunction that maps an instance of the problem to an instance of the solution can then be cast in the framework of Weihrauch reducibility. So P reducible to Q means that we can find Turing reductions. Phi is the reduction from of the problem. Psi is the procedure that recovers the solution. And the difference again between strong and weak, strong and the non-strong version is that in the strong version we are not allowed the access to the original problem when computing the solution. Okay, so how is this all related? Usually, if P is reducible to Q, usually one can turn it into a uniform proof of Q implies P. Of course, you have to check that that this induction doesn't go too bad. But usually, one can turn it into the principle Q implies P. So in the context of this Weihrauch reducibility, so I should also mention that in all the statements and all the results, they will hold both for the strong and the non-strong version. So I will not be so careful in distinguishing between the two. So in the context of what we just said, the two kind of little exercises that we have presented says that WKL is reducible to the 4-color theorem because you can convert a tree to the graph. And DNR3 is reducible to the 5-color theorem. Again, we have a graph that can decide a DNR3 function. So for the 6-color theorem, it turns out that you can reduce to the principal DNR4. Now for the 7-color theorem, you would expect DNR5, but for some strange reason, DNR5 doesn't quite work, but somewhat uncomfortably, we were able to show that DNR8 reduces to the 7-color theorem. But then now, you would expect for the 8 color theorem to have, okay, maybe here they like goes up by 1, and then here it goes up by 3, and then maybe next it should go up by I don't know, 5 or something, or something you can put in here. But actually it turns out that when we get to the 8 color theorem, it turns out that even the full DNR with no restriction on the range does not actually reduce to the 8 color theorem. Okay, so I'll just quickly give a hint as to why this is the case, and basically the easy explanation is just because 8 is equals to 4 plus 4. You can kind of do things first by looking at 4 colors and then filling in the rest of the graph with remaining 4 colors to diagonalize. So basically, suppose that there is a reduction, then what you can do is you can first color the graph with 4 colors, and then basically you use the fact that these theory reductions will have finite use, and then you can pad out the rest of the graph with G minus H being the rest of the graph with a different set of 4 colors, and that extends to an 8 color of the graph that doesn't compute a solution. So that's how we can use to diagonalize for the 8 color theorem. Of course, you can't do this with fewer than 8 colors, but you can do it with 8 or more colors. Okay, so what do we do for the 8 color theorem? So we know that DNRK does not reduce to the 8 color theorem for any K, in fact. So what we can do, what can we do? As it turns out, all you need is just more layers of non-uniformity. So we consider the following principle: DNRKL. So K is simply, again, the number of values that the DNR function is allowed. But now we have an additional parameter L. And basically, L stands for the number of times that the DNR function is allowed to change its mind. So G is a DNR function that is L approximable in the sense that it can change its mind up to L many times. Now, of course, it's unfair to allow the DNR function to change its mind L times without giving the universal function the opportunity to change. So we will allow the J to be replaced by a universal CE set with L plus 1 many possibilities, and we want G to avoid the set encoded by J of X. In particular, when L is 0, that's simply just the same as the DNR as the principal DNR K, right? And one can show that DNR K L plus 1 implies DNR K or DNR K comma L, which means that everything can be reduced all the way down to WKL. And furthermore, for any n, the n color theorem will reduce DNR K and Ln for some suitable parameters Kn and Ln. So this shows, in particular, that the n color theorem for any n is going to be equivalent, and this is again true for the other 2 principles with slightly different proofs. Okay, so that part is done as far as reverse mathematics is concerned, but that actually raises in our work that we consider a lot more questions. So for instance, all these principles with different parameters are actually have got very different ways of reducing to WKL. So in particular, for example, which ones of these are uniformly or computably obtainable from one another? So as an example, we saw that WKL is actually computably equivalent or Weihrauch equivalent to the 4 color theorem, but the 8 color theorem is not equivalent to WKL. So what about I don't know, maybe 5 or 6 or 7? It turns out for the 7 color theorem cannot be done, cannot be reduced computably as well, uniformly as well. Okay, so in the rest of the time, I think I will just finish up with just a discussion of this particular result, and then I will finish off with some remaining questions that we have. Okay, so we want to discuss why the 7-color theorem is not does not reduce uniformly to Weihrauch's lemma. First thing to point out is that we do have a reduction to DNR 8, so the diagonalization here cannot actually be the same as what we did for the 8-color theorem. Remember, for the 8-color theorem, the diagonalization was pretty simple because 8 was equal to 8 was 4 plus 4, so we can use the first set of 4 colors and then a remaining set of 4 disjoint colors to fill out the rest of the graph. Now that won't work here because DNR 8 actually is reducible to the 7-color theorem. So the diagonalization has to be a little bit more intricate. So the first claim is that in fact it suffices to reduce to the following graph, just purely graph theoretic fact. For any finite planar graph G extended by G0 and G1, so G is finite and planar, and G0 and G1 just have to be planar, they don't have to be finite. For any such 3 graphs, there is a 7 coloring of G that extends to 7 colorings of G0 and G1. In other words, equivalently, for any 3 such graphs, I can find a 7 coloring of G0 and a 7 coloring of G1 that are compatible on G. Now, it can be shown that this is in fact equivalent to the to whether or not WKL is Weihrauch reducible to the 7-color theorem. So you can replace 7 by any other number here also. Right. So why is this sufficient? So suppose we have this graph theoretic fact, and suppose that WKL does reduce to the 7-color theorem. And let's say that the reductions are phi and psi, phi going one way. So phi converts the tree to a graph, and psi converts a coloring of the graph to a path on the tree. Now, the first observation is that if we are thinking of feeding to phi more and more layers of the full infinite binary tree, 2 to the n, then phi applied to 2 to the n will be larger and larger pieces of the eventual graph. But there must be some n where on this finite graph, psi, which is the reduction back, must be total on every 7 coloring, because if not, then by compactness, or if you apply Weihrauch's lemma in the mathematical sense, you get a contradiction. Psi cannot work on some color of the infinite graph. So there must be already some level where psi has to be total. But all these ingredients are all computable. Psi is computable, phi is computable, and the input is computable. So you just search for this n. And once you get this n, you then take the graph G to be the output of the first n layers of the full binary tree. And G0 and G1 are just simply the 2 extensions of G, where in G0 we delete all the infinite paths extending 1, and in G1 we delete all the infinite paths extending 0. So G0 is in fact the full binary tree above 0, with 2 to the n, of course, to ensure extendability of G, of the input 2 to the n, and G1 to be the full binary tree above 1, but with the dead ends above level n. And by the graph theoretic assumption here, we can find H0 and H1, which are 7 colorings of G0 and G1 respectively, that are compatible on G. However, the assumption on G was that psi is total. So in particular, psi converges on sigma. But then now you get a problem because H0 and H1 both extend sigma. So psi has to be defined on H0 and H1. But then you get a problem because psi of sigma has to extend either 0 or 1, but then for example, if it extends 0, then psi of h1 will give you a contradiction, because psi of h1 is supposed to give you a path on the input tree, but on the input tree corresponding to h1, 0 does not extend to an infinite path on the tree. Right, so given this graph theoretic fact, in fact, you could prove that this graph theoretic fact is in fact equivalent to WKL not reducible to the 7-color theorem. One then can obtain this. Okay, so finally, we're going to just quickly describe why the graph theoretic fact is true. So the graph theoretic fact says that if I have any G extended by G0 and G1, all planar, then I can find colorings of 7 colorings of G0 and G1 that are compatible on G. So I think it's best explained with a diagram here. Little G0, so just the notations here. Little G0 is a fixed 4-color on big G0, which is this part, and little G1 is a fixed 4-color on 4-coloring of big G1, which we know exists because G0 and G1 are planar. And we simply produce the new coloring H in the following way. On the part where they intersect, which is here, G, we divide this finite part G here into 2 parts. One where the original G0 color takes values 0, 1, and 2, and the remaining where it takes value 3. And on the part here, we just take H to copy G0. And here we take H to copy not G0, but G1, but shifted by 3 colors, just to make sure that the 2 colors here do not conflict with each other, because we use different sets of colors here. And then they have obvious extensions to G0 part here and G1 part here. And then you can show that the defined color H is a 7-color which are compatible on G. So it's not yeah, it's just that 7, even though it's even though it's 4 plus 3, but 3 is enough for you to do this kind of extension. Okay, anyway, so what do we get from all of this? This shows that every 4 colors of every 4 levels of the K coloring theorem is proper. So 4n plus 4 color is not equivalent to any of the previous ones. And we can have similar extension theorem for the connected for the connected principle as well as the star principle. Recall that the star principle is the one with the computable diagram. We have similar extension results which are proved quite differently, but the statement is the same. And so now finally, as a corollary, we can show that for almost every K, the K coloring theorem is not the same as the connected nor the star coloring theorem for the same parameter K. Okay. Okay, so let me just finish off with some questions that we don't know the answer to. So recall that we just spent like the last 10 minutes discussing why WKL is not reducible to the 7-color theorem. On the other hand, it is equivalent to the 4-color theorem. So that leaves the question of 5 and 6-color theorem. So we do not know if the 5-color theorem and the 6-color theorem can be uniformly or effectively reduced to Weak-Koenig's lemma. The reduction we have is through DNR3 and DNR4, but we don't know if you can do it directly. A related question is whether or not any of the reductions within every 4 levels can that be made. So like, can the collapse actually happen between every other level? For example, we know that between every 4 levels, it doesn't collapse, but maybe some other reductions here is possible in between 4 levels, in between every 4 levels. We also do not know the relationships between the different parameters for the different variants of the k-color theorem. So, for example, for the k-color theorem, what is the smallest n such that the n star coloring theorem or the n connected graph coloring theorem reduces the k-color theorem. So we know that if n is 4, this is always true. And for n equals k, it is not true. But somewhere between 4 and k, there should be a reduction there. Now, the reason why this is not obvious is because if you have a graph, there is no way to effectively turn the graph into a, for example, into a connected graph. Because if you just add, if you just try to connect the different components, then you may connect it in a way that the graph cannot be extended to a planar graph. So the straightforward reduction doesn't work. Same thing with trying to deduce a computable diagram. Yeah, so there are other restrictions on planarity. So we've only considered restrictions on being connected and having a plane diagram, but there are other associated restrictions such as being locally finite or being highly recursive that can be considered, but we never did. What's also interesting is, I think I mentioned at the beginning of the talk that there is this Farey's theorem where every planar graph has an embedding with straight lines as edges. Now, the strength of that should be investigated. We don't know the strength of that particular theorem. Or, for example, related work for triangle-free graphs, which is also known as Groch's theorem, that every planar triangle-free graph has a 3-color. So that, I think, is also interesting to investigate. And finally, I think there are many experts here on the whole zoo of Weihrauch degrees. So we never really quite considered comparing these principles. So we were only focused with comparing the principles between the different parameters, but we never quite considered the relationship with other Weihrauch degrees. I think it could also be related to some ones, but you have to look at the principles which are I think reducible to Witt-Koenig's lemma for if you want to have a chance at this. Yeah, so I think that's my last slide. So yeah, thank you.
Question directly, or if I need to look at the chat, you may do better than me. Oh, please.
Quite early on, you said that if you've got a 2-colorable graph, which is computable, that then you would have a computable 2-coloring. That's clear to me if the graph is connected.
Oh, sorry. Yes, you're right. Yes. In fact, if the graph is not connected, then you could. Yeah, then it's not true. You're right. That there should be there should be a connected there. Yeah. When I went through the talk, I wanted to make the changes, but I forgot. Yes, you're right.
I see. Okay, good. Then we are on the same boat.
Yeah, it's somewhere.
Thank you. Any other question or comment? I have a naive question. Is there at least any easy negative result if you kind of ask for more effective reducibility notions? So you kind of, I don't know, you have some resource bound there that is bounded, such as time or something. Is it clear that some of these reductions are not possible?
Yeah. So we never formally actually studied this, but the reductions, or at least in the cases where we do have reductions, are pretty bad. So I think resource-wise, at least the reductions we had would be quite inefficient with respect to time or whatever. So yeah, so certainly that would be a good thing to consider. I think we probably would have to think of like cleverer ways to do the same thing. I guess. Yeah.
Any other question, comment?
Yes, I have another question.
Yeah, Vasco.
Vasco?
Yes, my question is related to your own last question. So
Yes,
do
I knew you asked.
My question is, do you know any uniform upper bounds? I mean, in those cases where WKL is not a lower bound, it's imaginable that you have better upper bounds. So for instance, can you exclude these DNR K principles as upper bounds?
Yeah. So all of the DNRK principles that we looked at were we just well, okay, so first of all, our interest, the reason why DNR even came up was because we were desperate to look for a way to reduce just reverse math wise. So we were just happy that we could do it, at least in some of the cases. So we did try to show that certain of the principles were not reducible to certain DNR, like for different combinations. But there the situation was a lot less clear. So the only thing is that DNR2 is obviously a trivial upper bound. But once you get to DNR3, it's not even clear that you can exclude that because, yeah, I mean, DNR2 is a special case because you could identify that with a path on the tree, and that's really the way we encoded like graphs into like, you know, but just with the DNR3, we don't know how to make the association. So yeah, so we did consider it, but it's not so clear.
But you have no argument that excludes it as an upper bound, so it could still be possible.
We tried to do either an upper bound or show that some combination is not an upper bound, but I think apart from the trivial ones, we don't have any results either way. Yeah.
Okay, thank you.
I would be interested, yeah, if you could, yeah, it's good, you know.
Thank you. So I think we're gonna take a 15 minutes break and come back about 1/4 past.